Hello there, welcome to Lab 4. My name is Noah Geiger, and let's just jump straight into it. Purpose of our lab today is to predict the behaviors of circuits containing resistors in series and parallels. We're going to be using multimeters to measure conventional current and potential differences in the circuits, and then we're going to examine the behavior of ohmic resistors and capacitors. Uh, some of our results is our final result was our RC value was 5.78 S. Three fundamental equations we'll be using is Ohm's law, which is delta V equals IR. The loop rule, which basically says the sum change will equal zero. And then we're going to be using the linearization formula, and that's going to be used for graphing. So circuit one, you can see here's a little picture of it. It's basically you connected two resistors and two batteries. We got with a 3-volt battery with 0 amp, we got an amp reading of 0.22 amps. And that was using the multimeters to measure. And you can see here we kind of marked our graph, and eventually this proves that that loop theorem is correct because it went back to zero. So you see here it goes up and then it goes back to zero, making the net total change zero. Circuit 2, we have a little graph here. So with a less resistant light bulb, able to charge faster and it discharged faster than when it had a higher resistant light bulb, as you can see here, 1724 comparatively. The reason for this, or the result was the more resistance you have in a system, the longer the bulb takes to charge and discharge, and this is because if there's more resistance, then it makes everything travel slower. So it's going to take longer to charge, and so it's going to take longer for these electrons to discharge as well. Circuit theory is very simple. You have the RC circuit here, and we graphed it with multiple data points to get our experimental RC of 5.78. We calculated our theoretical RC to be 6S, and our experimental was 5.78. So a little bit different. Reason for those discrepancies are probably just the multimeter is kind of old. We're using actual wires, which are just a little bit different. Could have been a grounding issue, etc. So what if you're doing this lab in real life? Oh, we can skip this part. If you did this lab with real circuit components and access to virtual circuit, and see if you can determine how it behaved differently from the real emitter you use. So a real emitter experiences internal resistance and that causes discrepancy, meaning the stuff inside might mess with it, even if it's only slightly, it'll build up. While as the simulation one will just not account for this discrepancy. So what if we're doing this lab in real life, which is kind of what we did. We use real batteries and charged real capacitors. How quickly would the ideal model predict the capacitors to reach full charge? A real capacitor would take longer, kind of like we were mentioning before. There is a slight resistance in the wires. So even though, the wires is conductive and, electrons are supposed to move freely, not everything in the world is perfect. So because there's slight discrepancies, it's not gonna give us a 100% accurate reading. Um, so yeah, no coding to this question, and yeah, hope you have a great day.